Hello, everybody. Greetings from Lewiston, Maine. Thanks for tuning in. And I wanted to just do a couple examples of a one-way chi-square. So this is another hypothesis test that we're adding to our toolbox of different things that we can do with data. This one is actually pretty different from the other hypothesis tests we've done. And the big reason is that the type of data that we would use with a chi-square are different from the other types of data we've done with hypothesis tests. So we've talked a lot about averages. In fact, all the hypothesis tests we've done so far this semester have been looking at averages. We have, starting with our one sample Z, we had a sample of data, we calculated an average, we had a standard deviation, and then we could do something, compare that average to something else, and then we had two averages with our t-tests, multiple averages with our various ANOVAs, and so that's been sort of the theme so far, and that's where things are different with chi-square. So with chi-square, we are not looking at averages, and the reason why is because we have data that can't be averaged. So when we first started talking about, I'll do some typing on here. When we first started talking about types of data, right at the very beginning of the semester, we had nominal, ordinal, used to be able to type, interval, and ratio. And so these different categories, and when we first learned about these, I said that the interval and the ratio scales, those are the only ones. We have equal intervals, we have with ratio, we have an absolute 0 point. We can create meaningful averages. So that's the type of data we've been working with before, either Likert scales or things we can count and then average together. So what happens if we don't have interval or ratio scales in our data? Like, let's say we have nominal data. We are categorizing things, and maybe we're assigning numbers to those categories, but they're just qualitative variables. We're simply trying to figure out how things are sorted into categories, and we want to do a hypothesis test on that data, but we can't really do anything with averages, so all the tests we've learned so far are not going to work for us. So that's where we need a one-way chi-square. So let's talk about our new Greek letter, chi. I'll try and draw, it's sort of a fancy X, and it is a squared value. So this is the Greek letter chi-square. And it is one way because just like with the one-way ANOVA, we have one independent variable. And then we're going to look at the categories of that independent variable, or the counting, the frequencies associated with that independent variable. And I'll get to that, I'll explain that in more detail when we get to our example here. So with a one-way chi-square, we have one independent variable, which is the type of category that we're sorting things into. And then with our hypothesis test, we're gonna see how many items are in each category. And we can say, well, that's what my sample looks like. I wonder if this is true at the population level. And so that's why we're doing a hypothesis test to evaluate our sample data and try and draw conclusions about the broader population that we did not collect data from. All right, so there's two types of one-way chi-square that we're gonna be talking about today. So I wanna do an example of each of those. And I already have my data set up over here. So let's clear some space and we'll get to work. Okay, so in this example, I asked people what would be your ideal spring break trip? And then the numbers below, so we have, that's our independent variable, is the ideal spring break trip. And it has 6 levels, 6 categories. So again, the vocabulary that you're using is really helpful to be clear about what you're using and to not get confused and to communicate effectively. So we have one variable, which is spring break destinations, and it has 6 levels, and that's effectively 6 categories. And so I just basically asked these people, pick one of these 6 categories. So I had 17 people say that the beach would be ideal. 13 people wanted to go to the mountains. We had 13 people who said they wanted to do a cruise as their ideal spring break trip. had some big city fans in here, go down, Portland, maybe even South Portland, get that big city experience. Disney was also popular. We had 8 people who said that the Disney trip would be a good spring break activity. And then one person was like, you know what, I'd rather just stay at school, don't have to deal with the stress of travel, save some money, and that's my ideal spring break trip. So we have these categories, which is our independent variable, and the dependent variable in a chi-square is kind of weird because it's basically just the frequencies, the counts, how many people chose each of these 6 categories. And so what we're going to do is, the first example we're going to do is the one-way equiprobable chi-square. And so what we're going to be doing is we're asking the question, at a population level, are people choosing these categories at a different rate from other categories? So obviously, where you don't have the same number for everybody, for every category, but this is just sample data. So I'm asking the question with my hypothesis test, if I were able to measure the population, would I in fact have equal numbers across all of my categories, or is there something going on at a population level that there's a difference? Obviously my sample is not equal, but I don't know if that's just sampling error or if there's something really going on at the population level. So that's what we're doing with our hypothesis test. And that's why this is an equiprobable chi-square, because we're testing whether the categories are equally represented at the population level. So to set that up, before I start getting into like the hypotheses and decision rules, I like to look at how we're going to evaluate this mathematically, because then the hypotheses and all that make a little bit more sense. So what we have here, the numbers, our actual data is what we call, oops, I'm gonna correct that, our observed. This is how many people were in our sample actually. And then we want to come up with a set of expected results, which is, okay, if the categories really were equally represented, then what would I expect to find? And so I can figure out my total n, try and draw somewhat legibly here. And so the total n, I can just add up all these scores. So I have 60 total people that I sorted into these categories, which means that if they were truly equally distributed, then I would expect to find 10 in each category. Pretend that's a 10, 10, and 10. So now I have my row of observed data, that's my actual sample data, and then I've created a row of expected results here, which is what I'm going to compare for each category my observed value to. And the way I'm going to do that is with my chi-square formula. So I'm not going to write it there because I want to save space. So let's go over here. So the chi-square formula is weird because we're working with weird data, but we're going to, meaning not averages. So it looks pretty different. We don't have standard deviations. So it looks pretty different from the other formulas. So we have the sum so this means we're going to do this for all of our categories of the observed minus the expected. We're going to square that difference and then divide it by the expected difference. And calculating the expected is pretty straightforward in this example, but I like to have a little formula. And so the expected, pretend that looks like an E. Wow, it's really hard to draw in this whiteboard. Let's try again. Expected equals n divided by k. So I have, as we talked about, 60 people by adding up all those observed values, and then I have k's, just like with the one-way ANOVA, how many groups we're splitting this into. And so 60 divided by 6 gives me the expected value of 10, and that's going to be the same expected value for every category. So I can go ahead and for each category, I can simply try and semi-legibly compare. So there's 17 minus 10 squared over 10, and to that I'm going to add 13 minus 10 squared over 10, another 13 minus 10 squared over 10 for the cruise people. Get my 8 minus 10 squared over 10, another 8 minus 10, and finally my 1 minus 10 squared over 10. So this sum is going to work out to be my overall test statistic, my overall chi-square value. So this works out to be 4.9, 0.9, 0.9, 0.4, 0.4, and 8.1. So the sum of all those is going to be my chi-square value, which is 15.6. So that's our test statistic. We're not really going to interpret this value specifically, but just like with our other hypothesis tests, we're going to compare that to a critical value, see if that reaches our threshold for rejecting the null hypothesis, and all that sort of thing. So now that we've talked about this calculation, and specifically we've talked about this O being our observed data and E being our expected data, we can jump back and actually plug in the parts of our hypothesis test that I skipped over. So if we wanted to do our hypotheses, we would start off like we've done before with a null, H sub 0 and H sub 1 for our alternate. And the null is saying that the observed equals the expected. And I have a little subscript J for both of those. And I'm going to say that that is true for all categories. So the way we write that in stat speak is we're going to say O sub J equals E sub J for all J. And J is basically like a substitute for, I'm going to do that for my first group and then for my second group and all that up to the total number of groups I have. And the null is saying that the observed is equal to the expected for all of my groups at the population level. And then my alternate is simply going to be that there's some inequality somewhere in there. So this is a not equal to for some J. And in order to reject the null, they don't all need to be different. You can see that I have, like we look at the big city and the Disney, the 8 is not that different from the 10. So it's unlikely that those are significantly different there. But in order to reject the null, all that is required is that some of the group's observed values are significantly different from the expected values. And so that's what I'm gonna be evaluating with my overall hypothesis test. The cool thing about these horribly scrawled hypotheses is that this is exactly the same for all chi-square tests. You know, for t-tests, we're always like, okay, what are the values that I'm comparing it to? And for even for ANOVAs, you need to know how many groups you were comparing. For a one-way chi-square, the hypothesis statements always look identical. So if you learn these, then there you go. You're ready to do hypothesis statements for any chi-square test that comes your way. We can do our decision rules. These are going to be very familiar. We're going to compare our p-value to an alpha value, just like we do with any hypothesis test. And so let's see, I'm doing here an alpha. What did I set up for my alpha? Let me look real quick. Let's do an alpha of 0.05 just to keep things exciting. And if our p-value is less than or equal to our alpha, we'll reject our null. Our other decision rule is going to be looking at our test statistic, the chi-square. We don't need absolute value signs around this because all of our values have been squared. So there's no way to get a negative chi-square value. So all chi-square values, so if the chi-square obtained is greater than or equal to my chi-square critical. And the way I'm going to write that is I want to have my degrees of freedom in here like I do with any good critical value. So I'm going to say my chi-square sub alpha, and I'm going to put in my 5 degrees of freedom. And if then I need to figure out the value, so I have a new table of critical values for chi-square, and I'm going to look that up here for my degrees of freedom and my alpha level to figure out what my chi-square value is. I'll go ahead and put up the formula here for my degrees of freedom. For the one-way chi-square, it's k-1. So since I had 6 groups that I've sorted my people into, the degrees of freedom is going to be 5 using that formula k minus 1. So let's see if I'm able to share my stats tables. Stats tables, here we go. So let's see where my chi-square value is. Oh, wow, it's all upside down. Here's the F table. Oh, my scrolling is just not cooperating. T table, here we go, table B5, the upper tail value for the chi-square. Let's see if I can rotate this. Rotate counterclockwise. Yay. All right, there's something that looks reasonable. So this looks like our other stats tables. We have degrees of freedom in our rows. So we're going to look for degrees of freedom 5. And then we have our alpha levels up here across the top. And so we're using an alpha 0.05, degrees of freedom 5. And so we're going to come down here and see that it's 11.070 is going to be our critical value. One thing I want to point out that's a little weird about this table is that there are some values that we've not seen, alpha values that we've not seen in other tables. And I'm not sure why, for example, we would ever use a 0.50 or some of these really high 0.90. So just be careful that you're finding 0.05 and not confusing 0.50 or 0.005, that there's some potentially misleading alpha values in these column headers. So, so we're going to find 0.05, degrees of freedom 5, so our critical value is going to be 11.070. So let's see if we can find our whiteboard again. Yay, all right, so it's 11.070, and that will be the threshold that we will use to reject or fail to reject our null hypothesis. Okay, so moving along then to our test statistic, which we've already done. So we have our chi-square obtained formula here. We figured out our expected value, and then for each of our 6 categories, we compared the observed to the expected, and we found that our total chi-square here is this 15.6 value. So the next thing we need to do is back to our table to figure out our p-value. So let's see if we can do that. Oh, much easier this time around. Okay, so here is our, we again, like we've done with other tables, we need to stick on that same row, degrees of freedom, and we're going to find our value, the 15.6. So, and see where that falls relative to our column headers. So here's our critical value. We've exceeded that. We've exceeded this next one. And even this one, 15.0 is not, ours 15.6 is between these two, between the 0.01 and the 0.005. So like we've done with other p-values, we're going to say that our p-value must therefore be between 0.01 and 0.005, and we're going to say it's less than 0.01. So back to our whiteboard and write that in. We'll say that p is less than 0.01. So clearly we're going to be rejecting our null. We already knew that because our obtained value is larger than our critical. And now we can confirm that our p-value is less than our alpha value. So we will be rejecting the null hypothesis here. So what does that mean to reject the null hypothesis? Well, that means that somewhere among these categories, our observed is different from our expected. Or to say this sort of in terms of our variable, we're going to say that the people's choice of ideal spring break categories are not equally distributed among people. And so some of these, at least some, possibly all, but at least some of these categories of these spring break destinations are chosen more than others, and some are chosen less than others. And so just like with our ANOVAs, we need to, now that we've rejected the null hypothesis, we need to do additional post hoc tests to figure out exactly what's going on and which categories are leading to this significant difference. And those post hoc tests in a chi-square are called standardized residuals. I'll go ahead and write that in here. Typing, good time. And so for my standardized residuals, I have a very similar formula to my overall chi-square, but I'm going to do this separately for each category. And so the standardized residual formula, I'll write up here, usually represented with a capital R for residual. And what we're going to do for each category, we're going to take the observed minus the expected and divide it by the square root of the expected. So now we're no longer squaring our numerator, so we now can have negative values. And if you look at it, it's kind of like the square root of our overall formula. We also took out the sum because we're going to calculate a different R value for each category. And so just to do some of these, we have the residual 17 minus 10 over the square root of 10. And then we have 13 minus 10, there's a minus in there, 10 over the square root of 10, and so on for each of these categories. And we're going to get a different value. To save you the terror of watching me try and scroll these out, I'm just going to go ahead and put in the answer. So 2.21 is the residual value for the mountains. The cruise, I'm sorry, 2.21 is the residual value for the beach. The mountains and the cruise are going to have the same value, which is 0.95. And then same for the big city and Disney, they're going to have a value of negative 0.63, negative 0.63. And then finally, my stay in school is going to be, let's see, let's go ahead and do this a better way so things are less confusing. I'll just write this residual value above the category because it was starting to get confusing even to me, and it's my own scrolling. So, all right, so 0.63. And then finally, we have a residual value of negative 2.85. So this is our row of residuals. So what do we do with that information? Well, again, these are kind of hard to interpret as individual numbers, but what we're going to be looking for is an absolute value that is 2 or bigger. And if for every category that has an absolute value residual that is 2 or larger, we're going to say that that category is the one that is significantly contributing to our overall significant effect. So we can see here's our beach, the mountains, and these guys don't really get up to that threshold. And then the stay at school is the other category that is significantly contributing. So now we have a better pattern, we have a better idea of the pattern of this significance. So we can not only draw a conclusion on the overall chi-square and say that yes, these categories are not all equally represented, but we can get more specific and we can say that people chose the beach significantly more than you would expect from an equiprobable distribution, and people chose to stay at the school significantly less than you would expect with an equiprobable distribution. So that would be the complete interpretation of this hypothesis test, this one-way equiprobable chi-square, including in the residuals. And just like with an ANOVA, if we had not rejected the null hypothesis, then we wouldn't need to do any residuals. We wouldn't do post hoc tests without a significant overall test. We would just know that, yeah, even though our sample data are not equally represented, that they're not so far from an equiprobable distribution that we wouldn't conclude that the population is not equally distributed. So, all right, so that's the first version of our one-way chi-square. And that's the equiprobable version where we want to see if all categories are equally represented. So let's talk about the other version of the chi-square, which is the non-equiprobable. So I'm going to clear up a lot of this and set up another example. I'm just going to clear everything. And it's gone. Wow. That feels so clean now. Okay, so let's get our label here. So we're going to do the non-equiprobable. And so this is still a one-way chi-square. We have one independent variable with at least 2 levels, and we want to compare our sample data to some other distribution. We don't think that things are going to be equally represented. That would be the first type of test we did, but we want to compare it to some unequal distribution and see if our sample data represent that unequal distribution. So, for example, I am curious if psychology majors have a different amount of occurrence of left-handedness and right-handedness than the general population. So let's set up some data here. So I have some lefties and I have some righties. I know there are people out there who are ambidextrous. I am envious and can't do that at all. I'm very strongly right-handed. But I talked to 31 psych majors and I found that 8 of them are lefties and 23 of them are righties. And I want to see if that's different than the general population. So this is a non-equiprobable chi-square because I would never be asking the question, do I have an equal number of lefties and righties? That would be a really weird thing to ask, that since at the general population level, there's many, many more righties than lefties. So instead, I'm going to do this as a non-equiprobable chi-square and compare this to the population occurrence of lefties and righties. And it turns out that in the general population, that about 15% are lefties. So I want to compare my sample data to that occurrence and see if psychology majors have a different occurrence than the 15% left-handed and therefore 85% right-handedness. So the way this impacts our chi-square is simply in the expected value. So I'm not going to take my total n. So our total n here is 31. I'm not going to take my total n and split it equally among my categories. That would be the equiprobable. Instead, I'm going to adjust my expected value for each category based on this general population value. So I'm going to fill in my expected, and that's going to be this total n times the population proportion that I would expect in that category. So I have 15% lefties, so I'm going to multiply that 31 times 0.5, and then for my expected value for righties, I'm going to bring in the 85%. And so what I'm going to find there, save some space here, is working out the math. This is about 4.65 is the expected value for my lefties, and that means that 26.35 are going to be my expected values for my righties. Okay, this is super weird. You can't have decimal values of people, but we're just going to use this for math purposes. So you can keep them as decimals and be comfortable with that. No need to round to whole numbers when we're talking about our expected values. And now we have a different method for getting our expected values. I can write up the general formula here, which is E equals our total n times pi. And this is, so total n is pretty clear, but pi is not our good friend 3.1415 and so on. This is the population proportion. So it's a population value, which is why we're using a Greek letter. So it's a population p, or proportion, of how many people we expect in each category. And so the big difference here with our non-equiprobable chi-square is how we get our expected value. We're using this different formula, and we're getting a different expected value possibly for each of our categories. But once we've done that, it's exactly the same as we've done before with our other chi-square test. We're going to use the same formula. We're going to calculate for each category the difference of our observed minus expected squared, and then divide that by the expected, and we have a sum, so we're going to add that up for everybody. So let's go ahead and do that. We have, for our first group here, we have 8. Wow, it doesn't look like a 4 at all. We have 8 minus 4.65 squared, all divided by 4.65. And then to that, we're going to add the difference of 23 compared to our 26.35. We'll square that and divide that by 26.35. So one thing that I just want to point out as a common mistake, you've put in the time to calculate the expected values, and so you know that it's different, but just make sure that you're carrying out that difference for each category. Sometimes it's easy to get in the habit of just going ahead and using the same one when you should be switching for every category that you're going between. And so when we actually calculate that out, I'll spare you the mathematical excitement. Our total sum for chi-square obtained is going to be 2.84. So that'll be our test statistic. Let's just jump back and fill in, as I said, our null and alternative hypotheses are going to be the same for all these, where we have O sub j equals E sub j for all j in our null, and then O sub j does not equal E sub j for some j. Our decision rules are going to follow the similar pattern. We're going to compare p to alpha. So let's do and keep with our alpha 0.05. We'll reject our null. And we're going to find our chi-square obtained and see if that's greater than or equal to our chi-square critical. So that's chi-square of alpha. We're using the same degrees of freedom approach. So here it's just a simple 1 because we have two groups. K minus 1 is 1 in this case. So using our table, which I will spare you the jumping back and forth between screens, but it's exactly the same procedure. And we find that our obtained value is 3.841, and we will reject our null. For the test statistic, we've already calculated that, 2.84. And so now we can evaluate this relative to our p-value. And let's go ahead and actually do the jump over to our stats tables. So we're on this top row, 1 degree of freedom. Here's 3.841, our critical value for 0.05. And we had a test statistic of 2.84. So let's see, that's going to fall between the 0.10 and 0.05. So we're not going to be able to reject the null in this case. And we're going to say our p-value is less than 0.10. That's the smallest number that we can, I'm sorry, the largest number that we can find here that we can say that p is less than. All right, back to our whiteboard. So let's go ahead and write that in here. P is less than 0.10, which is not going to be enough for us to reject our null hypothesis. So in that case, we can come to the conclusion that we don't have a significantly different occurrence of left-handedness and right-handedness among psychology majors than we do with the general population, that there is no significant difference here. If we had found a significant difference, we would again need to ask the question, should we do standardized residuals? With only 2 categories, we actually wouldn't need to do standardized residuals, even with a significant overall test, because we would know that you know, both categories are contributing to that overall result. So there's no need to do the post hoc tests to figure that out. But we failed to reject, so we would just say, yep, psychology majors have the same, are not significantly different than the general population in terms of right-handedness and left-handedness. So that is the result of that hypothesis test. There does exist in the world other chi-square tests. There's a 2-way chi-square, which, as you might imagine, has 2 independent variables. That's beyond the scope of what we're going to talk about this semester, but I'll put it out there in case you run into that in your methods class or doing your thesis or in other projects. But these 2 one-way chi-square are all that you'll be responsible for this week's quiz. And I put a problem set out on Lyceum. And so the big question you need to ask yourself is, am I doing a one-way equiprobable or one-way non-equiprobable? And so I wanted to just offer some quick tips on how to distinguish between them. And it's all in the research question. It's like, you know, we could have done an equiprobable with these lefties and righties, but that's not a research question that really makes sense, is that whether we have an equal number of lefties and righties. So what you want to be looking for in the example is that research question is, are you comparing, or do you expect that all groups are going to be equally represented or not? And the key thing is in the non-equiprobable examples, you have to have a specific non-equiprobable distribution that you're comparing your sample data to. So when I gave the additional information up here, that 15% of the general population are lefties, that is giving you the information that should be the big clue that this is a non-equiprobable chi-square, that you're, it's not just that they're not equal, but they're not equal in a specific way, and that those probabilities need to be expressed somewhere in the problem that you're being assigned to work with. So check that out if you're not sure exactly whether to do the equiprobable or the non-equiprobable version of this chi-square test. All right, so those are the examples I prepared. So check out the problem set online, and of course you can find me in my office hours on Zoom, and of course shoot me an email if you have questions, and I'm glad to find a way to get in touch with you and help you out. So that's all I've got, and thanks for tuning in, and I will talk to you guys soon.